Doug Shack-Schuber, Clunk. My nickname is Shack. Most people are disappointed to meet me in person, but Shack with a K. So Joe is going to do that. Joe also organized Meet the Experts, and so that's what the question and answer is going to be at that part. Larry Woodman is one of our kernel experts and lead developer in VM, so he did the first part with us, but he's going to be available for question and answer. And without further ado, I'm going to introduce, so I mentioned a little bit, here's the agenda, and I mentioned how the TuneDs have evolved, and so the bottom right-hand corner is this new CPU partitioning TuneD that you might be interested if you're after ultra-low network latency. So this section, it's over to Sanjay on disk and I/O database performance.
All right, so you guys can you hear me in the back, right? Yep. So like Shaq said, so the default profile in Rails 7 is the throughput performance, and we found that some of these settings that are mentioned here, which are applied as soon as you select this profile, work great for most database workloads. I'm going to talk in context kind of because I/O is one of the main constraints that limit database performance. So a lot of the tuning that I'll talk about for the I/O stuff revolves around database, but I do help out with a whole bunch of other stuff in Shaq's team. So this is the default setting for databases, but we did find that there are several things you can do in order to improve performance of databases. So one of the things you can do to improve the performance of database, you can flush caches. Okay, this is specific to memory tuning. I know a lot of people run database during the day, but at nighttime they run backup workloads and some other type of workloads which tend to fill up the page cache. And next day when they resume normal operations, there are a bunch of user processes that come in and they are starved for memory, and they start forcing things into swap and things like that, and things are off to a sluggish start in the morning. So typically this is a kind of a quick way to mitigate that problem, and you can actually free up all the page cache that's used by other applications, and it'll release all that memory so that new processes that are coming in will find free pages and will be able to get going as soon as possible. This is the per file system flush daemon. In fact, I think this. I'm going to talk about the swappiness and the background ratio because per file system flush daemon does not apply that much to databases if you're typically using direct I/O. This is only applicable to databases that tend to use the file cache. And in order to tune this, actually, the follow-up is in the next page. How many people run Oracle databases here? And if you see, he talked about transparent huge pages in the first section of this talk. They always recommend that you turn swappiness to 0. That is the reason why I have that up there. In Rel 6 and Rel 7, you really don't have to do much with this particular parameter. But what this parameter basically does is it changes the behavior of the system in how it reclaims pages. So if you have a busy system where you've got a lot of users coming and going all the time, and you want to make sure that they find free pages when they enter the system, you want to set the swappiness low. And that's the reason why Oracle used to tell people to set swappiness to 0, so that pages can be reclaimed and be available on the free list for new user processes as they come in. But the two processes that I'm mainly going to talk about in this next slide is the dirty background ratio and the dirty ratio. This one affects many of our customers, and we run into this time and again because you have a fairly large chunk of your memory allocated to your database, right? I mean, you start with an SGA of 70% of your physical memory, and then the remaining 30% is available for your user processes as they come and go. On certain busy days, if your user count suddenly goes through the roof, one of the things we notice is you hit up against these limits. How this works is, I've kind of tried to illustrate this, that when your system has less than 10% of the RAM is less than 10% of the RAM is dirty, you're practically doing nothing. But as soon as you start exceeding that 10%, which is the value set by dirty background ratio, flush D wakes up and starts writing those dirty buffers onto the disk and starts freeing up that memory. But as soon as you hit this limit, the dirty ratio limit, which is set to 20%, your system actually stops processing in order to make sure that that threshold is not crossed. And processes start doing synchronous writes out to the disk. How many people have encountered systems where you're running a database and suddenly things get sluggish? it's non-responsive, right? I mean, we run into this problem all the time, especially when the system tend to get busy. This is one way to kind of alleviate that problem. The easiest way to do this is try to write as many, flush as many blocks as you can in the background. So you lower dirty background ratio on to maybe 5%. You can go, on large systems, you can go as low as 1% so that flush D wakes up and starts flush, especially on busy systems. And typically, I don't recommend increasing this because you don't want that much dirty ratio, dirty buffer sitting on your system because the system crashes. That can be a really bad thing. Normally, you would hope that the system won't crash, but I usually don't recommend bumping this up. But in certain cases, we've found that increasing that has also helped separate that gap where you don't hit that dirty ratio limit. Swappiness, I just mentioned this. By decreasing this value, you can do more aggressive reclaim of unmapped page cache memory, and you can delay swapping. Because when it comes to databases, swapping is bad. This slide actually talks, one of my favorite tools when I actually try to look at a full system view of what's going on in a database environment. And you can see here what I've tried to do is capture the VM stats when I had an old TP workload working in a fiber channel environment. And I've used different color schemes to kind of show what I'm monitoring. I've got my memory numbers right here. Good news is I'm not swapping because I've got a bunch of free memory. This is the I/O that's going on in the system. But I just want to draw your attention to this section where you'll see that there's a whole bunch of numbers in the wait column. And although my system is showing a whole lot of CPU idle, it can be misleading. People look at these charts and they go, oh, I have a lot of idle CPU on my system, and yet my performance kind of caps off. I tell them to pay attention to the wait column. If you are seeing a whole bunch of wait, you can actually go and look at your database statistics, and it will tell you exactly why you're waiting. There can be queries that are waiting on results and things like that. And in this case, what I found was when I looked at the database stats pack, that my log file syncs were taking a long time because my I/O was not able to keep up. When I switched that same exact database to a faster SSD environment, you can see all those waits have disappeared. My idle has gone practically because now my system is spending more time doing actual work. This is the exact same database doing the exact same activity, and just by identifying that I was running on slower devices and by moving to faster devices, I was able to fully utilize my system, so to speak. This is an example of how we use solid-state devices. We get really ultra-fast devices now. We had some NAND devices, and now the 3D cross-point Optane devices gave me a nice bump from 800,000 transactions to more than 1 million transactions per minute. And we also have been experimenting with NVDIM, and you can see by using NVDIM devices, just by putting my redo logs, which tend to be the most costly I/O, tend to have the most costly I/O requirements. By moving just my redo logs to my NVDIM devices, I was able to actually double my performance and go almost up to 2 million transactions per second. The graph is kind of hidden, that's why you don't see the number, but I was able to go from 1 million to 2 million transactions per second. And TuneD profile, just now like Shaq said, throughput performance is typically good for most database environments. But one of the things we saw recently with one of the customers was their DB2 workload was not utilizing CPUs. So what happens in those situations is if your the workload doesn't get your system busy, the CPUs tend to clock at a lower speed when you're running in a throughput performance profile. All systems nowadays are designed to run in kind of a quasi-perform, power savings mode. So if you need to run at the highest speed possible at every, just if latency is important to you, then you can choose a latency performance profile, and you can see here, as my system got busier, the difference in performance was not much because the CPUs got clocked up. But when my system was not that busy, I was actually able to improve performance by choosing latency performance. So this is crucial for people who have systems that are lightly to medium loaded, and yet they want to run at the highest possible frequency. We recommend that they choose the latency performance profile. One more feature which is in RHEL 7 is LVM cache. How many people use LVM for their databases, volume managers? Quite a few. I mean, I know a lot of databases provide their own volume managers, but if you're using LVM cache, we actually now have a feature that will let you utilize faster devices to cache your LVM. So it acts as a front-end cache for your LVM devices and gives you significant speed up. In this case, I'm running the exact same workload. I run my LVM, I attached a fast device to my fiber channel LVM storage. And you can see with my fiber channel storage, I kind of top off performance. But as I add the LVM cache, in a write-through mode, I was able to get a nice chunk of performance improvement. And then LVM cache also runs in a write-back mode. I was able to get my performance even better. So write-back mode is essentially things get cached in the faster device, and they don't get flushed out. So, and because it's a solid-state device, you don't have to worry about data persistence. Even if the system goes down, all that information is still there on the faster device. So it gives you a significant speed up. So I encourage, if you're running LVM, I encourage you to look at that. And the last one is hyperthreads. I get this question repeatedly, like, when should I be using hyperthreads in my environment? I mean, my hardware gives me the ability to run hyperthreads. Does it really help performance? So we ran a whole bunch of tests, and what we found was when you add additional threads to your workload, if it's not unable to share the CPU cache, we talked about NUMA extensively in the first half. If it's not able to share the CPU cache, adding more threads to do a workload really does not benefit you much. But if you are able to take advantage of NUMA and share the CPU cache, that's when you get the best bang for your buck. So what we found was by using proper NUMA alignment, when I was putting things on a single NUMA node, I saw 30% gain. But as I started spreading the workload out, now they were contending for CPU cache. They were crossing NUMA boundaries. I found that I was getting less and less advantage of using hyperthreads. So that is the reason. That's one more reason that if you're running multiple workloads on a system, to use NUMA. And in those situations, you may also benefit from turning on hyperthreads. So yeah, I think that's it for the database stuff. I will pass the baton on to Joe. And if there are any questions, like Joe said, after the room clears up, please come and talk to us. We'll be here for the expert session.
So I'm going to talk about a few features that help latency network performance. Here we go. We have a low latency tuning guide on our portal, and it was the first two versions were written by Jeremy Eder. He did a lot of low latency work, and I picked it up about a year and a half ago from him. It was a reference Bible for low latency tuning. And I suggest if you're interested in low latency, please go read it. The link is there, and it goes through all the steps. Things get a whole lot easier in RHEL 7. I'll mention that in a minute. Again, I'm going to cut to the chase. Back in RHEL 7.2, people were saying, gee, I have to go to real-time kernel in order to get rid of, not only for determinism, but to get rid of some jitter. And if you look, on the left-hand axis, the y-axis, we have microseconds of latency. And you could see that the real-time kernel along the bottom was quite quiet, like 10 to 12 microseconds tops. And the RHEL 7.2 kernel had spikes well up into well over 100, 140 microseconds. And the question was, what do we do about it? And we came up, people said, I don't want to run the real-time kernel. How do I get rid of those latency spikes? This is one of the things in RHEL 7 is the ability, our system clock ticks, interrupts your processes 1,000 times a second to do housekeeping tasks. And one of the things that, if nothing's running, then you'll have no tick. But if you have a user space task running, you'll tick 1,000 times a second. And that can get intrusive. That takes you off the run queue and disrupts your CPU caches, and then you come back on. So, and that also affects jitter. So the question was, what do we do? In RHEL 7, we came out with no hertz full, and that says if you're the only one running on that CPU, then you'll only be interrupted for a clock tick once per second, not 1,000 times a second. And if you have more than one process running on it, then you're back to 1,000 ticks a second. But those ticks are for timekeeping, the scheduler load balancing, and memory statistics. So here's a graph of it, of no hertz full. Here's your task is interrupted here, and then for all the times where you would have had a tick, your green user task can run seamlessly and continue running on. That takes care of a lot of, that not only helps with performance, but takes care of jitter. How many of you are familiar with the ISO CPU's boot line flag? A few. It's a way of saying, I want everybody off of these CPUs, because I want to dedicate them to my application. Unfortunately, when you do that, there's no load balancing. It's great if you're pinning your processes. For example, if you say, all right, I want to isolate these 4 CPUs in green, you add this flag to your kernel grub line, and when you're running, you pin your application to those. You have, let's say, 5 threads, and you pin them to each CPU, and your application runs seamlessly, and the kernel keeps things away, and life is good. That's just what I just said a minute ago. You task set it, and you run it, and everything's good. If you do not pin your application, let's say you isolate 5 CPUs, and you say, all right, application, go run on those 5 isolated CPUs, they're all yours. Your entire application, all the threads will execute on the first CPU, and the other CPUs will be idle. And the reason is there is no scheduler load balancing that occurs on isolated CPUs, because the scheduler load balancer takes about a 40 microsecond hit, and that latency, if you're using isolated CPUs, you want low latency, and you can't afford that hit. So if you're an application that can pin your CPUs, great, but if you're a larger application, what do you do about it? And we had this problem for OpenStack with virtual network functions, had a problem where they said, hey, I have these, let's say, look at this big chunk of green CPUs here and a big chunk of purple CPUs here, where the VNF NUMA threads on each node. We have poll mode drivers in green. We have QEMU emulation processes. They needed quiet CPUs. They needed, so they wouldn't have, this might be a DPDK underneath. And the idea was, how do we do this? We had no mechanism. Plus, in OpenStack, it's really not conducive to going down and touching everyone's grub line and rebooting. So the answer was the new CPU partitioning profile, and it came out in RHEL 7.4. What the nice thing about it is, if you go back to this and say, all right, on this node, CPU 0 and 40, and on this node 20 and 60, those will be the ones where I want all the overhead tasks, all the kernel tasks, everybody else to go sit on those CPUs, and I want all the rest quiet for my application. So you decide which CPUs, like in that case, there's one configuration file, and you specify in there the CPUs you want to isolate. And if you also want no load balancing on them, because you say, hey, I'm going to pin on these 1 or 2 CPUs, I don't want the load balancer interrupting, you can say also no load balancing, because I don't want those interrupts. You then set your tuned to CPU partitioning profile and then reboot. I don't know how many of you have set a system up for low latency performance. If you set one up once, I've done a lot of them, you always fat finger it and cause problems, and you have to go in and double check and look that I get it right. And sure, once you get a system right, you can script it and get it perfect, but it seems like every time you're turning around to a new system. This does it automatically under the covers. When you reboot, I'll quickly go through the set of steps that are done. All the CPU affinity mask for all the user processes and all the kernel processes that can be moved are moved off those CPUs. You can read the steps here. A whole lot of things needed to quiet down those CPUs. And many of the things that were mentioned before in other TuneD profiles are also set. The governors are set for power, for performance, and all these tunables. It is really popular. And how many of you run tests where they're noisy? You run them over and over, and if you're running for performance, they're variable and you get noise. One of the things we learned with this partitioning profile, suppose you say, it doesn't even have to be a big one, but suppose you say, hey, I just need 5 CPUs for my test. You can set TuneD, this profile, to say, hey, just give me a handful of CPUs over here, reboot, and now you can run your test to task set it to say, run on those quiet CPUs. You'll be amazed at the quietness of your performance test when you run on those quiet CPUs. That was a nice surprise out of this. How are we doing on time? Some general guidelines for low latency performance. For the sake of time, I recommend you read that book. All these slides will be available. There are a couple of key features I want to cover, performance features that we use frequently and get a lot out of. One is Tuna. Are you familiar with Tuna? It's available on RHEL 6 and 7. It's a way of looking at your system and saying, are my CPUs pinned to the right, where are all my CPUs allowed to run? Who else is running on the CPUs I need quiet? And where are my IRQs? Do you remember Shaq mentioned before that if your devices are on a certain node, you want to make sure your IRQs are happening on that node, co-located with your devices. Tuna is a way of doing that. The command line interface for it is right here. You can see a lot, very quick. If you want to move, like this one here, all IRQs, ETH4, and then a wildcard, away from NUMA node 1, because let's say that's a network interface you don't care about, that one command will do it. And there are a whole lot of commands, things you can do with Tuna. After I set up a system, I always go back in and use Tuna just as a visual. Here I sort the affinities, the IRQs on the number of events, and I see the hottest IRQs on the system, and I have the names, and then I look and see what CPUs they're allowed to run on. And that is a confirmation to me that says, okay, I know that that named device lives on this node, and those are the CPUs on that node, and that's where I want it to run. I can also see which CPUs are busy during the test, and I can say, hey, wait a minute, why are those busy? I didn't want that to happen. And then down here, every single thing on the system, I can look and say, who else is allowed to run on the CPUs I want quiet, or who's colliding with me? And then if you want, you can actually take a whole lot of the system tunables and configure them with sliders, get your system running the way you want it, save it, and you can make your own TuneD out of it, customized. How many of you are familiar with CPU cache line false sharing? We have a few. It's a tool that we developed and we added to the perf tool at Red Hat, an enhancement. And let me just show you a picture of what CPU cache line false sharing is. When you go to the CPU to read a variable, let's say you want to read that int A, you don't just get that integer when you do a load of A. You get the whole cache line, 64 bytes, pulled into your CPU from memory. Well, suppose that cache line is being shared. Suppose there's a pthread mutex in the cache line and also a sequence counter in the cache line. Every time someone modifies that, you have to throw away your copy. You could be in a loop reading A over and over again, and every time someone modifies, let's say, the lock or the sequence counter, you have to throw away your copy and get back in line. And this is just an example of a lot of CPUs accessing that cache line, and we've seen performance plunge considerably when there's a lot of false sharing. If you're running a shared memory application or one with a lot of a multi-threaded application in a NUMA environment, this is a great tool to go in and look and see who is tugging on each other's cache line, and it gives you all the information needed to pinpoint and say, here are the hottest cache lines, And here are the offenders, here's who's reading and writing, and here's all the information I need to go right into the source code to figure out, to take steps to triage it. How are we doing for time? A little bit. Shaq mentioned earlier the numastat program, and that's a great way of looking and saying, all right, where is all the memory for my process? What that doesn't tell you is, when I execute a program, what CPU and NUMA node did I execute on, and where did I get the memory from? And because if they're co-located, that's great. If you're always reaching across to another NUMA node for your hot performance-sensitive programs, that can hurt you. A couple of easy ways to get to find out where your program, your CPU is executing, is to take the PS command, and with that syntax, it'll actually list the last ran CPU. So this is a sampling. Or you can run the top command, enter F, and select the last use field, and that'll propagate up. What I like is to use the perf tool. There's something called perf mem, and it will show you the node and physical it'll show you the node, the virtual address, a whole lot of information about all your loads and stores, and you can get a sense of, okay, here's where I executed it, and here's where I got my memory, but it doesn't quite yet give a great picture of where I got my memory. There's a coworker who's enhancing it. It'll be in an upcoming release of RHEL 7. He's modifying it to get the physical address information. So now you'll be able to see, like, run it on your program, and you'll get a snapshot for, here are all the loads in my system, here's a NUMA node they executed on, and here's the NUMA node where the memory actually lived. And you can do some sort on the output and look and say, wow, 30% of my loads are going across to a NUMA node. And you can look at the function names that it's happening on and say, wait a minute, those are my hot functions. Why are my hot functions constantly going over to another NUMA node? And this is a great way of doing it. We have a lot of customers who want to get rid of every last cycle, wasted cycle of their application, and this is meeting their requests. Noisy neighbor. Intel came out with cache allocation technology, and CAT and CMT for monitoring. It was started available in Broadwell. Skylake came out, and then they found out it doesn't work in Skylake, so it's temporarily off in Skylake, but it'll be on after. And the idea is, suppose you have on the left-hand side, a low priority program, a mem copy or B copy or just any kind of copy. It's filling up your last level cache. And you have a high priority program here who's trying to do stuff, and every time it's trying to use its data that's in the last level cache, it's been wiped out by your low priority and high priority. So with this technology, you can say, hey, low-level program, I don't care how fast you run. You might be doing backups or something. You get a tiny fraction you can specify. You get a tiny fraction of the last level cache. And then your high-priority program has the bulk of the last level cache. Its data stays there, and it runs a lot faster. And this is a textbook case of LM Bench where it measures the speed to go out to memory. And I ran a program in the background that does dirties memory. And sure enough, you can see on the left-hand side, it's the latency in nanoseconds to go out to go to memory. And without CAT, you can see how high the latency went as I increased the megabyte, the data size I was trying to read. And you can see with CAT, when I took that noisy neighbor pig program that was dirty, and I moved them aside and said, you only get a tiny bit of the last level cache, you can see the speed of the memory references just the plummeted. So the performance improved significantly. That'll be available. If you're on Skylake, it's not available. And check.
Thanks, Joe. Yes, so Joe rocketed through, I guess, the advanced course in networking, and definitely he's working on the tougher problems for networking, but basically those were all around low latency, and in fact, NFV is one area of optimization there. I am going to just rewind really quickly, because there are some other just high-level things that might help you also for, you can see in the first section we went through how most of our tunedies are either latency or performance, and so we've been concentrating on, you know, the really hard problem, the ultra-low latency, digging into the details that have been going on and making sure we can have tools to expose them. Throughput's very important, so as the networks have gotten from 10 gig now to 40 to 100 gig networks. The throughput performance, a lot of people used to do manual tuning of the send-receive buffers, various things. The kernel developers are trying to make that automatic, right? Because Red Hat isn't just used on bare metal or even KVM Vert or anything. It's actually used up as guest in clouds, as guest in various subsystems. So these tunedies do adjust various parameters. Again, went to 10 gig. The network stack guys said we don't need send-receive buffers modified. It went to 40 gig. They said, oh crap, we do actually still need some of the limits bumped up. So I recommend you trying these. Obviously, setting things like jumbo frames. Make sure they're set on your host and your guest if you're in a VM, but also make sure the switch is set properly to be able to aware. So basic things like that. It's usually easier to try to get the bandwidth, the throughput problem, than the ultra-low latency. So the final thing that it happens in the tunedies is we start adjusting the processor's ability to wake up, and it's mostly power savings. And so on the x86 architecture, it's the C states, right? So how often do you wake up from a sleep, and lower is better, in fact, and you can see these transitions. When I started the thing, you saw the jiggity-jaggedy, this is your brain, and this is your brain on tuned, and it flattened out, right? So that's basically what was happening. A good portion of that is we're manually adjusting the C states, and so you're not always going to get the same power savings. More and more, some of our tunedies are zeroing in on altering the default C state to save power, because there's been a race to save power, and yeah, we can indeed be the greenest operating system, but when you paid for those servers at 3 gigahertz or whatever, sometimes you actually want your network I/O to actually give you the 3 gigahertz, and you don't have to have every core busy to do that. So network I/O, maybe you use 2 or 3 cores. We're finding 10 and 40 gigs. I'm sorry, 40 and 100 gigs. You actually probably need more than one core. So multi-queue came about in Red Hat 6 and Red Hat 7 for networking. It's coming out in the final topic I wanted to jump in. If you're familiar with OSs in general, Joe jumped in and shared you how we went to a tickless timer. But the same thing's true with I/O drivers. If the driver can see that you're busy all the time, rather than interrupting and disturbing that determinism again, it will actually, you can set it up to automatically go into what we call busy pull, and you can check if your device supports this. We need support in the driver for these, and so you can take a look at the ethtool commands right here to check in on that. So lots of cool stuff besides the ultra low latency, and with that, I'm going to fast forward. We do want to save some time. There's just 3 slides on NFV. This is mostly a telco. Today, NFV, Joe mentioned the low latency tuning guides. Jeremy Eder was the first author. he's still actually with Red Hat, so that's great. And he's actually bringing low latency to containers with Kubernetes plugins, and performance-sensitive applications are actually in OpenShift 3.9. DPDK and OVS are actually used in OpenStack as well, and a lot of telcos have built a model with kernel bypass technologies like DPDK. And what that means is they have a VM, and the VM has special lanes to help the poll mode drivers. So same thing, we don't need to interrupt. In fact, we cut out a good portion of the network stack. That's why they call it kernel bypass. And they can run these cards now, and instead of 1 million packets a second, you can get 10 million packets a second through this. So it's not just a little 5% improvement in performance, it can be an order of magnitude. So here's the difference, the final chart. So yeah, we get paid per chart. So we actually have backup charts at the end of the deck that we're going to share with you, but we're going to pause here. You can see the blue lines are what the vhost user DPDK can achieve in packets. The blue is, the bars are actually million packets per second, so 12 million packets a second. And the kernel is the orange. So now the kernel guys, again, not to be outdone, you see upstream development on a thing called XDP, and XDP is eventually going to allow you to keep a TCP/IP stack and approach these type of numbers here in the future. So you can see as the packets get bigger, there's not a huge advantage. I also showed CPU usage here, so you can see by not interrupting in and out of the kernel, the green bar here, and this is percent utilization, shows what the kernel is costing you. But remember, you're getting a lot. DPDK is not something you just turn on and you forget about. You have to write your application to call it. So don't think, oh, we just need DPDK everywhere. So this is mainly around packet processing for telco, maybe for 5G or for other technologies here in the future. And that's a whirlwind tour through networking and disk-I/O. There's lots of documentation and updates. Tuning is a full 1-week class at Red Hat. It's RH442, I believe, if you guys feel like taking digging in. And again, a lot of what we're doing should apply bare metal, but does apply to VMs or containers as well. Remember, VMs are just processes running on the operating system. The same tools manipulate them, like in the first part, with NUMA control, etc. Containers are also, it's process-based, and in fact, when you share your workloads into a container, we are seeing almost very minimal overhead between bare metal and a container, because a container is just a process running on a Linux host.